would show up as small distortions of either this or this part of the projected lensed galaxy. So we are kind of looking for inconsistency between this image and this image in a very subtle way. And of course we are not the only ones, so it's a hot problem, many people are working on this. And why it's interesting is that there is just the expectation that for cold dark matter there should be lots of substructure. For warm dark matter models, the substructure should be suppressed. So if you can show that your lensing system doesn't have any substructure at some level, you can rule out cold dark matter. Then maybe it's their neutrinos or something like that. What's really hard, really hard about the problem is that in order to calculate the probability of your model, of the image that you see, it's not enough to, of course, know the dark matter properties, but you need to also marginalize over all the source parameters, you need to marginalize over all the dark matter subhalos, and a machine learning person would call this process intractable. So it's just a very hard integral to do in practice. And one way to do it is to train a neural net to do the integral for you, kind of. So this is an example by Bremer et al. And Kyle Kramer and Gilles Loup and others. They use what is called likelihood-free inference techniques, which we started using for other projects, to kind of do the marginals. So they simulate a reasonably simple lensing system with a simple source and a simple lens, but with lots of substructure along the line of sight. And they train the neural network to directly, by just looking at the image, reconstruct substructure parameters. So the fraction of dark matter that is in substructure plus the slope of the subhalo mass function. And this works, but we kind of tried to, so this works on these simple images, and we could discuss if this works on also more complicated sources. We had quite some discussions in the last 2 days when I was in New York. But the thing that I tried and that we tried in my group was to actually get to the sources, to get to the halos itself. And this is just a horrible problem. So you can try it with Monte Carlos. We tried lots of things, I'm not going through this. In the end, what we ended up doing is to just try to get a good fit to the data in the first place. So to do map estimation. And this means instead of actually trying to sample from the posterior and then marginalize our source subhalo positions, we simply fit it. And this here is, again, this posterior here, it would be marginalized over subhalo properties. Here it's just without the integral, and finding the map estimator just means we find the best possible fit for all the individual halos, and the lens, the source parameters, as well as the subhalo mass function. Okay, so that's one can do this, and one of the things we did as well was, you don't know how many subhalos there are in the lensed image. So there could be one, there could be two. In principle, if you just think about a galaxy with subhalos, there are thousands. So to avoid the problem of actually jumping between the number of subhalos back and forth, which would be not possible really in this auto-differentiable frameworks, we just wanted to simulate a lot of subhalos. So the task was to write an analysis pipeline that doesn't linearly scale with the number of subhalos that we include. And that's surprisingly simple if you use PyTorch, because we just use fast Fourier transform on CUDA, on GPU, and that is blazing fast. So we can literally simulate millions of halos really fast by just putting like lots of little dots in a like big image, then fast Fourier transform and multiply with fast Fourier transform and FNW halo, NFW halo, or the displacement field of this, and then fast Fourier transform back. And then you get like the column density, column mass of lots of halos, column density mass of lots of halos. And the nice thing is you can just autograph the entire thing, so it's easy to calculate the gradient of this mass distribution with a million halo parameters. We don't need a million halos, but we need 1,000 or so in our tests. Next problem is if you just calculate the best fit value for the masses of halos, most of these subhalos would actually not be constrained by data, because they sit in regions of the image where you don't have a galaxy, right? So they would sit like, they would sit here, or they would be just tiny and not affect the image in the first place. So what happens in that case, annoyingly but not surprisingly, is that if you calculate the map estimator, all these subhalos just zip to the most probable value from the mass distribution. So they all run against the median of your, not median, what is this? The mode, thanks, mode. The mode of your prior, and that's it. And then you get like a crappy nonsense mass distribution with lots of halos here and 2 or 3 here. So that doesn't work either. However, what we found, and I think we are the only ones who did this up to now in the context of astronomical image analysis. I actually found no example for this anywhere. What we found is that if you now enforce the point cloud of halo masses to have high entropy, so if you introduce like an additional entropy term, this here would be differential entropy, and you switch off all data, so you just want to maximize the probability of halo masses and entropy at the same time, you end up with halo masses that are nicely distributed as your prior, over your prior. And the reason is that, the reason why this works is twofold. First, one can show that this basically is equivalent to enforcing that the distribution function, the empirical distribution function of your fitted halos. So you think of this as the individual halo masses, and you just run like a kernel smoothing over this. So that the difference between this empirical mass distribution and the prior mass distribution is minimized. This is Kullbach-Leiberg divergence. So that's one way to think about it. Another way to think about it is that this entropy term is kind of equivalent to combinatorial factors that you would get if you would take into account that halos are indistinguishable, so you could just swap 2 and get the same configuration as you had before. And effectively what we do is to introduce like a repulsive force between individual halo masses. This is coming from, so yeah, we use, in order to calculate entropy, we use this Kotsashenko-Leonenko entropy estimator, which was proposed in some Russian journal in the 80s. I don't know who found this. I don't know my master's student, but we did quite a bit into like how to estimate entropies of point clouds. But anyway, the cool thing is it basically is just a sum over the log of nearest neighbor distances. And if you take the gradient of this, you basically get a 1 over d repulsive force between individual halo masses. And so this means this thing will just, these masses will just repel each other and distribute nicely over the mass distribution. And then you can get a fit to the data that actually makes sense. So if you fit then to the data, you get first a distribution of halos and a galaxy, a source galaxy that looks like the data in the first place. But you also get a halo mass function that looks realistic. And this is just a toy example, really toyish example, where we have a fixed source and fixed mainlands. We just distribute like 1,000 subhalos. Here not real distribution, but we just kept them in the region where they would be visible. And they all have free mass, so this is a 1,000 parameter fit. And what you see here is, so most of the masses would be so small that these things are not detectable really, but a few of them, so around 10, 20 will be with masses above 10 to the 7 solar masses. And what you see here as horizontal line is the position of the subhalos in mock data. And what you see is vertical line is the position of fitted subhalos, all above the threshold of 10 to the 7 solar masses. And you see the fit picks up where the subhalos are. Not always the right subhalos, but like sometimes it's 2 instead of 1, and sometimes the mass is a bit wrong, but it's roughly kind of right. And if we now actually look at, and what one now can do is, okay, we can just take this as a possible fit to the data. You don't have the entire posterior, you just have like one peak in the posterior of the problem, and look at the hyperparameters of the problem. So you can play with the halo mass function. And what we found, at least for our toy examples up to now, is this actually works. It works for simpler toy examples that have nothing to do with lensing, but it also works here. And for instance, if you generate images where we have a cutoff scale at like 10 to the 7 solar masses, and we fit this with our procedure, we end also up with cutoff scales around 10 to the 7. And here we get deviations because typically there are less than one halo with 10 to the 9 in our images, so it doesn't work too well. But it works quite well as in this particular example. There are lots of caveats because we still keep here the source fixed, which is like really stupid because that's not how reality works, so we don't know the source. And we have, and what we encounter is as soon as we actually model the source, there's lots of substructure that we mismodel, and this all like wants to be absorbed with subhalos. So we have to now, as a next step, understand again better how to regularize sources at different magnifications. But the statistical method itself works, and it's quite powerful. And I mean, it looks maybe a bit weird, and it's like, okay, maximum entropy, this has been done in the 90s, so why is this interesting? But it's interesting new twist to maximum entropy as far as I can tell. So traditionally, when looking for maximum entropy, regularization of like X-ray images or gamma-ray images was what's a good thing to think about is what's the maximum entropy solution in absence of data, right? That's kind of the question. You want to have a solution which corresponds to maximum entropy and which you would run against if you wouldn't have data that pulls you in another direction. And in this traditional approaches of maximum entropy in the context of image analysis, the maximum entropy solution is just a flat image. It's just, if you don't have data, your result will be a flat image. And any data will try to deviate, will push you towards deviating from that. And the reason why this was used, probably is still used sometimes, is to reduce the effects of overfitting. That's one of the reasons. The way we use actually, and the reason is here maximum entropy is actually applied directly to the expected flux in individual pixels. We apply maximum entropy here directly to the model parameters, which is a completely different thing. And this means typical maximum entropy solution in absence of data will be just a random sample from our generative model. So a maximum entropy solution will not look like this, but like a lensed galaxy with subhalos in it. And we look for deviations from that model if we do a fit to the data. So that seems to be a quite powerful technique to my mind to, in general, study, if you have to study a population of a large number of objects, whereas a large number of them is actually not observed.